In this video, we're going to talk about concavity and second derivative test. Notice these three graphs of f. They're all increasing. Do you see any difference between these three graphs? It turns out this one, we call it concave up. And this graph, f, is concave down. And this graph has no concavity. How do you know whether it's concave up or down or no concavity? If you draw a tangent line to a point, and if the graph of f is above the tangent line, then we say it's concave up. Notice this tangent line right here, and there's a graph f. This graph is below the tangent line, that's why it's concave down. And this one has no concavity because if you draw a tangent line, there's no graph above or below, so there's no concavity. Now let's take a look at these three graphs of f. They're all decreasing. What can you say about this graph? If you draw a tangent line, you notice that graph is above, so it's concave up. What about this one? You draw a tangent line, the function f is below the tangent line, so we say it's concave down. And what about that one? You draw a tangent line, there's no graph above or below, so no concavity. So the first derivative, the f prime, tells you when f is increasing or decreasing. Now, in order to find the concavity of f, we have to look at the second derivative of f, which is f double prime. So let's take a look at definition of concavity. The graph of a differentiable function y equals f of x is concave up on an interval I if y prime is increasing on that interval. If y prime is increasing, this implies that y double prime has to be positive. So whenever y double prime or f double prime is positive, that means f is concave up. Now it's concave down. What do you mean by it? Y or f of x is concave down on an interval I if y prime is decreasing on that interval. Now, when y prime is decreasing, that implies that y double prime is going to be negative. So in other words, if y or f is a twice differentiable function, then f or y is concave up on any interval where y double prime is positive, and y or f prime of x is concave down on any interval where y double prime is negative. So let's take a look at y equals x squared from interval 3 to 10. What can we say about the concavity? Well, in order to find out the concavity, we need to find the second derivative. So y prime will be 2x, and y double prime is 2. So let's take a look at the y double prime chart. And you try to set it equal to 0. However, everything is positive. No matter what x is, y double prime is always positive. So this implies that y equals x squared will always be concave up because y double prime is positive. So within the interval 3 to 10, you know that the y equals x squared will be concave up. As a matter of fact, it doesn't matter what interval it is. Y equals x squared will always be concave up since second derivative is positive. Now let's talk about the concavity of y equals 3 plus sine x on the interval from 0 to 2 pi. So let's find the second derivative. In order to do that, we got to find the first derivative. Root of 3 is 0, and root of sine x is cosine x. And the second derivative will be negative sine x. Now, when is the second derivative equal to 0? Let's divide by negative. You get 0 equals sine x. And you know that sine x equals 0 when x equals 0, pi, 2 pi, and so forth. We could stop right there because we're looking at the interval from 0 to 2 pi. So let's come up with the y double prime chart. We have 0, pi, and 2 pi. What is a nice number from 0 to pi? How about pi over 2? Now, this is a second derivative chart, so make sure you use the second derivative. So plug in pi over 2, sine of pi over 2 is 1, so you get negative. What about 3 pi over 2? Sine of 3 pi over 2 is negative 1. Negative 1 times negative is positive. So as you can see, y is concave. Now remember, when we talk about concavity, we're talking about the concavity of y. So y is concave down from 0 to 2 pi. Pi. And y is concave up from pi to 2 pi. Now notice, the sign of y double prime changes when x equals pi. It turns out this is the inflection point, which we're going to talk about. And here's a definition of point of inflection. A point where the graph of a function has a tangent line and where the concavity changes is a point of inflection. So in order to find point of inflection, you first need to find when y double prime is 0 or when y double prime is undefined. Very similar to finding the critical points. But for critical point, we use y prime, not y double prime. And not only that, we also have to check the sign of y double prime changes, either positive to negative or negative to positive. And we call that point a point of inflection. And we'll take a look at some examples. Let's try to find the inflection point and look at the concavity of y equals e to the negative x squared. Before I start, notice that e to the negative x squared is same thing as 1 over e to the x squared. So no matter what x is, this will always be positive. Plug in a negative number. Negative square will be positive. And what about 0? E to the 0 will be just 1. So 1 over 1 is 1. So therefore positive. So keep that in mind. So let's find the first derivative. You get y prime is negative 2x e to the negative x squared. And let's find the second derivative. We have to use the product rule, so you get negative 2x times negative 2x e to the negative x squared plus e to the negative x squared times the derivative of negative 2x, which is negative 2. So you get 4x squared e to the negative x squared minus 2e to the negative x squared. That's the second derivative. You could take out the greatest common factor, which is e to the negative x squared, and you're left with 4x squared minus 2. And in order to find the inflection point, we need to set that equal to 0 or find out when this is undefined. Now, so this happens when 0 is equal to e to the negative x squared, or 0 equals 4x squared minus 2. In order to solve for x, you have to do natural log both sides, but we have a problem here. What is natural log of 0? It's undefined. So you cannot solve this. Remember, e to the negative x squared is always positive. You can never equal to 0. So this one we cannot solve for x. What about over here? This will be 1 over 2 equals x squared. So therefore, x will be positive negative square root of 1 over 2. So these are our possible inflection points. Because in order for inflection point to occur, the sign of y double prime has to change. And we need to check that. So you get radical 1 over 2. And you have negative radical 1 over 2. Now remember, this is a y double prime. So we have to use this one right here. This was our y double prime. So you might want to forget about the 0 now. You might want to plug in the number to see what kind of sign you get. So what's a nice number to try over here? Maybe 10. Plug in 10. Now remember, this is always positive. So you'll get a positive times positive, which is positive. What about here? 0. Plug in 0. You're going to get negative. Because negative times positive is negative. What about over here? Plug in negative 10. Positive times positive is positive. So based on this, we know that y is concave up from negative infinity to negative radical 1 over 2. And radical 1 over 2 to infinity. Those are the intervals where y is concave up. And y is concave down from negative radical 1 over 2 to radical 1 over 2. Now, what is the inflection point? Inflection point is when x equals negative radical 1 over 2. And how do you find the y value of the inflection point? You have to plug it into the original. And it turns out it's going to be e to the negative 1 over 2. Also, the other inflection point will be radical 1 over 2. And you plug it into the y. You end up getting e to the negative 1 over 2. So therefore, you have two inflection points. And let's take a look at f of x equals 1 over x. How can we find the inflection point of f of x? Let's find the first derivative. I want to rewrite it as x to the negative 1. I mean, you could apply the quotient rule, but I like to work it like x to the negative 1. So you get negative x to the negative 2. That is the first derivative. And what is the second derivative? Second derivative will be 2x to the negative 3, which is the same thing as 2 over x to the third. Now, when is this equal to 0? Well, if you cross multiply, you get 0 equals 2, which is not true. So this will never equal to 0. Now, when is this undefined? The second derivative is undefined when x equals 0. Because when x equals 0, the denominator becomes 0. So this is our possible candidate for inflection point. So let's draw f double prime in this case, because we're using function of f. Now, 0 is our candidate. So what happens when you plug in a number that's greater than 0 to second derivative? You get positive. What about negative? You get negative. So sign does change at x equals 0. However, what happens when you plug in 0 to the original? It's undefined. So therefore, we don't have point of inflection for f of x. Because even though sign changed, when you plug in 0, we cannot find the y value. However, we could find the concavity. From negative infinity to 0, f is concave down. And from 0 to infinity, f is concave up. We can use second derivative test to find local extrema. If you recall, we used the first derivative test to find local min and local max. But we could also use a second derivative to find the local max and local min. And this is what I mean. If f prime of c is equal to 0, which means that there is going to be a horizontal tangent line when x equals c. And if f double prime of c is less than 0, which means second derivative at c is negative, that means f is concave down. Then f has a local maximum at x equals c. So this point right here becomes a local maximum. And number 2, if f prime of c is equal to 0, again, there's a tangent line at x equals c, horizontal tangent line, and f double prime of c is greater than 0. That means the second derivative at x equals c is positive, which means f is concave up. Then this point right here will be a local minimum of f. So at local minimum, the first derivative is equal to 0, and the f will be concave up. At local maximum, the first derivative is equal to 0 because you're going to have a horizontal tangent line at that point, and the graph of f will be concave down. It says find the local extreme values of f of x equals x cubed minus 12x minus 5. And since we just talked about finding the local extrema using second derivative test, and let's use our second derivative test to find the local extreme values. So in order to do that, we need to find the first derivative. To find the critical point, you get 3x squared minus 12. And what is the second derivative? It's going to be 6x. And how do we find the critical points? Set equal to 0. And you get 12 equals 3x squared. Divide both sides by 3. You get 4. So you get x equals positive negative 2. These are critical points. Now, originally, if you don't want to use a second derivative test, you have to come up with the f prime chart and see where sign changes. That's how you find local min and max. If you want to use a second derivative test, and by the way, you have to know how to use a second derivative test to find the local extreme values, because on the AP exam, sometimes they design the problem so that you won't be able to find the first derivative, but they give you information about second derivative, and based on that, you have to tell whether f of x has a local extreme values. So make sure you guys understand about the second derivative test to find local extreme values. So what happens when we plug in this critical point to second derivative? Let's plug in negative 2 first. You get negative 12. This means that second derivative is negative, which implies that f is concave down. This is f. So that point will be a local maximum. So we know that local max at x equals negative 2. And if you want to find the y value, plug it into the original. Now what happens at 2 now? Plug it into the second derivative. You're going to get 6 times 2, which is 12. When the second derivative is positive, that means the f is concave up. So that means that point right there will be a local minimum. So local min at x equals 2. And if you want to find the y value, when x equals 2, you got to plug it into the f of x.